Hello, my name is Sophie Kohler, and today I'm going to be showing you how to solve this problem right here. The strain rosette shown is used to measure the strains on a structure made of AISI 302 stainless steel. Gauge 1, which is the pink right here, reads -300 times 10 to the -6 inches per inches. Gauge 2, which is green, reads 200 times 10 to the -6 inches per inches. And gauge 3, which is the orange, reads 425 times 10 to the -6 inches per inches. Find the principal stresses as well as the shear stress max. We are going to report our answers in KSI because since these are inches per inches and is in the US customary system, that means that we will be reporting the stresses in KSI. So first, what we have to do is we want to find the strain in the X direction, the Y direction, as well as the shear strain by using the strain rosette equations. Now, the strain rosette equations, I will write them out right here. So for the gauge 1, oops, pen is not working. Gauge 1 equals strain in the X direction times cosine squared. The theta, so since the theta that is measured from the X direction to the gauge that we are measuring. Since we are measuring gauge 1, we want to have the theta be measured counterclockwise from the X direction, which would equal theta equals beta, equals 360 minus beta. We see right here that beta is 75 minus 75. So the theta that we would put in here is, is 285 degrees. Plug that in, 285 degrees. Then we do plus the strain in the Y direction of sine squared, same angle, 285 degrees, plus shear strain times sine 285 degrees cosine times cosine 285 degrees. Now, if you plug in for the strain, -300 times 10 to the -6 equals. So one very important thing to take a look at here is that since E2 is up against the x-axis, that means that I'll put it right here. E2 equals EX. This is very important because it simplifies the equations in the math that we have to do. So we can plug in for strain in the X direction, we can plug in strain 2, which is 200 times 10 to -6. If we calculate what this value is, cosine 285 squared, we find that it equals 0.067 plus the strain in the y direction times, if we plug this into our calculator, we end up getting 0.933. And lastly, for the shear strain, we get negative 0.25. If we simplify this equation and move this term over here, we end up getting equation 1, which is 313.4 times 10 to the negative 6 equals 0.933 strain in the y minus 0.25 strain xy, shear strain xy. This is equation 1, and we would want to save this for later. Now, if we want to, since we already know that gauge 1, now for gauge 2, since we already know that gauge 2 equals strain in the x direction, then we are done for gauge 2, and we do not need to plug it into this equation. For gauge 3, we have 3 equals strain in the x direction, cosine squared theta 3 plus strain in the y, sine squared theta 3 plus shear strain xy sine theta 3 cosine theta 3. So, since this angle is measured counterclockwise, that means that we can keep the 75. So if we plug the 75 in for theta, as well as the 200 in for strain in the x direction, and the 425 times 10 to the negative 6, and for the gauge, then we end up getting this equation, which I am writing out right here. We get 425 times 10 to the negative 6 equals 200 times 10 to the negative 6 times cosine squared 75 plus strain y sine 75 squared plus shear strain sine 75 cosine 75. This equation ends up becoming 411.6 times 10 to the negative 6 equals 0.933 strain in the y plus 0.25 shear strain. This will be equation 2. Now that we have 2 equations and 2 unknowns, then we can solve to find these variables. It is solvable. Going over to the next page, and I will write these out again. So we have equation 1 equals 313.4 times 10 to the negative 6 equals 0.933 strain in the y minus 0.25 strain or shear strain. Then equation 2 equals 411.6 times 10 to the negative 6 equals 0.933 strain in the y plus 0.25 shear strain. Now, if we try to combine these equations, we see that the shear strain cancels out. Now, if we add these equations together, we can solve for the strain in the y direction. So on this side, you get 725 times 10 to the negative 6 equals 1.866 strain in the y. Strain in the y equals 388.5 times 10 to the negative 6 inches per inches. Important to keep this, so I'm going to box it. Now, if you plug this back into one of these two equations, we can solve for the shear strain. I am going to plug it back into equation 1. So 313.4 times 10 to the negative 6 equals 0.933 times 388.5 times 10 to the negative 6 minus 0.25 stress, or not stress, strain, shear strain. Now, if you move this variable, not variable, but numbers over to here, and divide by 0.25, we end up getting the shear strain equals 196.4 times 10 to negative 6 inches per inches. Now that we have the strain in the x direction, the y direction, as well as the shear strain, then we can use Mohr circle to find what the principal strains are and the max shear strain is. So then we can use the equations to convert it into the principal stresses. First, what you do is you plot these points. The first point would be strain in the x direction as the x coordinate, and as the y coordinate, it would be negative strain divided by 2. And this is the first point. The second point would be strain in the y direction, positive xy over 2. Shear strain divided by 2. This is a positive. Shear strain divided by 2 is a negative. We want one positive and one negative because when we graph this solution, we want the line that intersects both points to also intersect the axis of strain. Now, I am going to draw a grid with strain and tau, or not tau, strain and strain in the x. Perfect. So we find that equation 1, or not equation 1, but point 1 is 200 times 10 to the negative 6 and then shear strain divided by 2 equals 98.2. This is 0.1. 0.2 equals strain in the y direction, which we have solved for right up here, equals 388.5 times 10 to the negative 6, positive 98.2. Now we draw it on here. So 1, 2, 3. This is a negative 98.2. 1, 2, 3. Positive 98.2. Then for 0.1, 200. It's negative, so this is 0.1. Then 388.5, positive 98.2, and this is 0.2. Once you have the points drawn, then we want to connect a line between them. As I was saying before, we want one point to be negative and one point to be in the positive y direction, because this point where it intersects, where this line intersects, is strain average, the strain average. To find the strain average, we want to I'm just going to rip it so you can see. To find the strain average, we want to do strain average equals strain 1 plus strain 2 divided by 2. Strain average equals 200 plus 388.5 divided by 2. Strain average then equals 294.25 times 10 to negative 6 inches per inches. Now that we have the strain average, we want to make a circle connecting these points together. So to do that, move it down a little bit. Do that. Try your best to create a perfect circle. And that's a little wonky, but it's okay. So now what we want to do is we want to find the radius. But the reason why we want to find what the radius is because at these points where I'm Xing, these are the principal strains. Put it right up here. Principal strains. Sorry, principal strains. To find the principal strains, we want to find what the radius is, and then either add the radius to the strain average or subtract it from the strain average. To find what the radius is, I am going to be using a green highlighter to show you. We can do Pythagorean's theorem by creating this triangle. Perfect. So we know that the height right here is 98.2, and the length right here is 388.5 minus the average, which is 294.25, to which equals 94.25. Perfect. So now that we have that, we can do Pythagorean's theorem, which is R equals square root of 94.25 squared plus 98.2 squared. The radius equals, after plugging in the calculator, 136.11 times 10 to the negative 6 inches per inches. Now that we have what the radius equals, we can solve for the strain minimum and the strain maximum. So, to do that, to solve for the strain minimum, we do the strain average minus R. Strain minimum equals 294.25 times 10 to the negative 6 inches per inches minus 136.11 times 10 to the negative 6 inches per inches. So the strain minimum, or the minimum strain, is 158.139 times 10 to the negative 6 inches per inches. To find the strain max, you do the strain average plus R. This is because this strain average is in the center of the circle, so if you add R to it, you'll be able to get to the circumference of the circle, which is right here. And if you subtract R from it, you'll also be able to get to the circumference of the circle, which is right here. That is why this equation works. Sorry about that. So the strain max equals 294.25 times 10 to the negative 6 inches per inches plus 136.11 times 10 to the negative 6 inches per inches. And if you plug that in, oh, I made a mistake, this is 4. If you plug that into the calculator, you get the maximum strain equals 430.36 times 10 to the negative 6 inches per inches. Now that we have what the minimum and maximum strains are, we need to find the shear strain maximum. The shear strain maximum is going to be the tallest one, or the tallest point on the circumference and on the circle. So since this is going to be the highest point from the center of the circle up, will be R. So we can conclude that tau max divided by 2, since these are divided by 2, equals R. We found up above here that R equals 136.11 times 10 to the negative 6 equals tau max divided by 2. We find that the shear strain, sorry, I said tau max, but shear strain max equals 272.22 times 10 to negative 6 inches per inches. The Morse circle is very important in demonstrating how to find what the maximum and minimum strains are and shear strains are from any given any given strain in the x direction and any given strain in the y direction. You can also use Morse circle to Morse circle to find what the principal stresses are if you started off with stress. Now that we have the principal strains, which is min and max, as well as the shear strain max, we need to convert these into the principal stresses and the principal stresses. To do this, we use generalized Hooke's law. So I am going to go like this, go like this. So generalized Hooke's law. First, to be able to use this, we need to look up some property components of AISI 302 stainless steel. We want to find what the modulus of elasticity is, as well as the modulus of rigidity is. And from these two, we can find what Poisson's ratio is, which is this. So let me get my book. So if you flip to A12, Appendix B, you scroll down and you find that the modulus of elasticity is 28 times 10 to the 6 psi. The modulus of rigidity is 10.8 times 10 to the 6 psi. And to find the Poisson's ratio, which is the V right here, you do modulus of elasticity divided by 2 times the modulus of rigidity minus 1. So if we plug in these components into here to find Poisson's ratio, it would be 28 times 10 to the 6 psi divided by 2 times 10 to the 8 times 10.8 times 10 to the 6 psi minus 1. We find that Poisson's ratio equals 0.3. Now that we have Poisson's ratio, we can transform the strain min, max, and shear strain into stresses. So for changing into stresses, the principal stress of max or the stress 1 equals modulus of elasticity divided by 1 minus Poisson's ratio squared times strain max plus Poisson's ratio times strain min. Okay, so we take our what is given. So we have stress 1 equals 28 times 10 to the 6 psi divided by 1 minus 0.3 squared times what we found up here. The strain max is 430.36 times 10 to the negative 6 inches per inches plus Poisson's ratio 0.3 times the min of strain, which is 158.14 times 10 to the negative 6 inches per inches. Once we plug this into our calculator, we find that stress 1 equals 11.78 KSI. Now, to find the strain or the stress minimum, or also known as stress number 2, we do equation, again, modulus of elasticity divided by 1 minus Poisson's ratio times, now this inside's going to be a little different. Oops, sorry, you can't see it. To find the min, or the second stress, you do modulus of elasticity divided by 1 minus Poisson's ratio times strain min plus Poisson's ratio times strain max. Now, you do the same exact thing that we did for stress max and plug in all the known variables. So we have strain or stress min equals modulus elasticity, which is 28 times 10 to the 6 psi divided by 1 minus 0.3 squared times, we have the strain min, which is 158.14 times 10 to the negative 6 per inches, plus Poisson's ratio, 0.3, times the max, 430.36 times 10 to the negative 6 inches per inches. Now, if we plug this into our calculator, we find that the principal min stress equals 8.84 KSI. Now, lastly, we have to solve for the maximum shear stress. So, this is what we do. We do tau max equals modulus of rigidity times the shear strain max that we have calculated with the unit circle that is right here. So, tau max equals modulus of rigidity, which we found to be 10.8 times 10 to the 6, 10.8 times 10 to the 6, times shear strain max, which we found from the unit circle to be 272.22 times 10 to the negative 6. And I said unit circle, I mean Mohr circle. Sorry about that. Now, we find that tau max equals, plug that in our calculator, tau max equals 2.94 KSI. So now that we have solved all the problems, I am going to rewrite the answers that we have gotten. The question asks us to find the stresses 1, stress 2, as well as tau max. From us using the strain Rosette equations to find the strains in the X, Y, and shear strain, we were able to use the Mohr circle to convert those into the maximums and minimums of strain and shear strain. Then, once we found the principles of the strains, we utilized generalized Hooke's law to transform strain into stress. So, we have found that stress 1 equals 11.78 KSI. Stress 2 equals 8.84 KSI. And tau max, or shear stress, equals 2.94 KSI. Now that is one way how you solve a strain Rosette problem to find the principal stresses. Thank you very much.